All right, everyone, let's continue. We are down to 2 more chapters in this course. I know you're worn out. I'm worn out. Everyone is just kind of enough with the semester. We want it to be done. So I hope we can together get through it. These are difficult chapters. I'm not trying to scare you, but I'm trying to get you to try to be engaged, because we might be picking up the pace a little bit on some of the topics, because we're gonna rely on many of the subjects we discussed earlier in the chapter, specifically linear systems of equations. They're gonna come back over and over again. Okay, but these 2 last chapters are very important. They get you closer and closer to kind of what these fancy looking solutions that you see, researchers show. We're getting there. We're getting to that point. Okay, we will start with nonlinear solvers, which, like linear solvers, okay, we studied how, I don't know what's wrong with me today. We studied how to solve linear systems of equations, and at least subsets of those. Now we're going to study techniques to solve nonlinear systems of equations. But we're going to start with solving a single nonlinear equation, because getting to the nonlinear system is going to take us some mathematical magic to do. Okay. Learning objectives, again, helps me anchor what I want to teach, and helps you anchor expectations. At the end of this chapter, you should be able to do the following: define what a nonlinear equation is, and define by what we mean when we say solve f of x equals 0. What does that mean? Okay. Define and write down the residual form of an equation. That's a new term you haven't probably heard of. Define what is meant by the root of an equation. You already know that. Define closed and open domain methods for solving nonlinear equations. This might be new. Calculate the roots of an equation using the bisection, false position, and Newton's method. Those are 3 methods that we're going to learn. We're going to learn how to use to solve nonlinear equations. And then the beast in this chapter, define a system of nonlinear equations. Remember nonlinear regression. We said we know how to write the system of equations for nonlinear regression. We just don't know how to solve it yet. In this chapter, we're going to learn how to solve it. Learn how to linearize a system of nonlinear equations. Everything is based on linearization. We take that nonlinear system, we make it linear, we solve the linear system, rinse and repeat. Okay. Calculate the roots of a system of nonlinear equations, and geometrically interpret the roots of a system of nonlinear equations. It's one thing to interpret the roots of a single equation with a single unknown. It's another to interpret the roots of 50 equations with 50 unknowns. Okay, what does that mean? And finally, define the Jacobian matrix of a system of nonlinear equations. Okay, we will start with an example. I tried to do some fancy graphics. We have this parachutist coming down through the clouds, yay, and yeah, let's do it again. Yay. Has anyone here actually come down through a parachute? Kevin, twice. Like in what context? Skydiving. And your cousin? Wow. Yeah, I don't know how people do that. Anyway, so this parachutist is coming down through the cloud, and the parachutist is subject to Newton's law, right? The body and the parachute, this entire structure, is subject to Newton's second law of motion. Okay, summation of forces on this entire object is equal to the mass times the acceleration. U is the velocity, du by dt is the acceleration. Okay, how is the rate of speed increasing as the parachutist comes down? Okay. Now, in terms of forces, we have the weight force, right? Caused by the attraction of the Earth. That's the total mass. Okay, we assume that the mass of the parachute is negligible, but it's not. But for simplicity, this is the mass of the
Dr. Saad, your sound isn't coming through on Zoom.
Batteries. Okay, thank you for letting me know. I appreciate your letting me know. Again, I cannot see your chat, okay? But thank you for speaking up. Okay, let me see if I have an extra battery here. Let me see if it can do it with one battery. All right, can you guys hear me on Zoom?
Yep, all good now.
Okay, so hopefully this will last. Please speak up again. I ran out of batteries. I charged them, but they did not fully charge, I suppose. All right. So with this object, you have a larger drag coefficient. It's kind of obvious. And for this profile, you have a smaller drag coefficient. But all of this can be formulated as F as the drag force being a function of the velocity. Now, when you plug that in, you have Fd plus F sub u equal mass times du by dt. And you solve for the velocity, for the speed of the parachutist, you can get an exact solution in this case. U of t equal mg over the drag coefficient into 1 minus e to the minus c over mt. So m is the mass of the parachutist, g is gravitational constant 9.81, c is some constant value, and u is the velocity. Okay. So now I'm gonna ask you this question. Suppose you have a parachutist whose mass is 70 kilogram. Okay. And suppose you know the velocity. Okay, so you know u of t, and you know the gravity, you know m. Suppose you know the drag coefficient. And my question is, for a 70 kilogram parachutist, what is the required drag coefficient, okay, to reach a velocity of 40 meters per second after 10 seconds of descent? So you're given u of t, you're given t. Okay, so what I'm trying to do here is I'm trying to design a parachute. Okay, I'm trying to design a parachute. What that means is designing C, really, going after C. I'm trying to design a parachute such that I'm targeting 70 kilogram parachutists, such that they reach a speed of 40 meters per second after 10 seconds of falling. So you have G, you have M, you have U, and you have T. Okay, my question is to find C. So try to extract C from this equation. Okay, plug in some numbers, play around with the formula, and try to extract C from this equation. Don't look at the slides. And really, the numerical values do not matter. I'm giving you numerical values to say, assume you know U, T, M, and G, find C. So in other words, I'm asking you to express C in terms of all the other quantities. So extract C out of this equation. Because designing a parachute is equivalent, you know, to designing a parachute with a specific drag coefficient, so that you target a certain descent rate. That's how they do it for the Mars rover. Okay, and they run these experiments like in underwater and other kind of crazy fluids. Nathan, you got it? Tell me. No way. What? Well, no, that's find it analytically, Nathan. You gotta find it analytically. You're using a nonlinear solver. I'm teaching you about that. I want to teach you how to make your own Excels. But actually, keep that answer in mind, because we're going to compare it to what we get with Python, okay? But try to do it by hand. Try just to solve it by hand. Okay, so what would you use in Python to figure it out?
Well, I would make some space T or C rather, and would plug in for each of the variables, put in one of dots, and get output u. And then I would take the log of the equation to get it into a linearized format.
Do you think you'll be able to linearize this one?
Take log of both, and then you could get close to it. Yeah, you get it. Yeah.
Okay, I disagree. Okay, but that's the whole purpose of why do we need fsolve, right? That's the entire point. So don't use fsolve, don't use Excel, don't use your fancy calculators. Just try it by hand to extract C. Okay, so let me be more clear here. Okay, now it should be clearer. Do this analytically by hand. It's pretty annoying, right? Yeah. Well, you can step back and ask yourself, is this, why is it annoying? Because whatever you do to it, like you take a log, you subtract, you divide, you can't extract C out of it because C shows up non-linearly in this equation. So really, you cannot extract C out of this model because no matter what transformation you do, think about nonlinear regression, no matter what transformation you apply to that formula, you cannot extract C out of it, okay? And this is what I have on the next slide. This is actually unsolvable by simple algebraic manipulation. You can use perturbation theory, etc., but we're not talking about that. We're talking about just taking this model and trying to pull C out of this formula. You can't do it by just simple algebraic manipulation. This is because C appears in a nonlinear fashion in the governing equation. Okay, all right. So now we're gonna switch back and forth between this example and some theory so that we can learn how to come back. Our objective is to eventually find that C, extract that C numerically, okay, in a smart and efficient way. So far, you know how to solve a single linear equation, like ax equal b. You say x equal b over a. You know how to solve linear systems of equations, A matrix, A equal B, X is A inverse B, right? Or whatever iterative solvers you use. In this chapter, you will learn how to solve nonlinear equations that can be arbitrary. We cannot write them in like a single form, okay? They're just crazy nonlinear equations, okay? Such as this one, log x plus cosine x e to the minus 0.1 x equals 0, okay? But what's a nonlinear equation or function? And we keep coming back to this kind of idea of linear and nonlinear. And in a way, it's like you get to know it just by experience. But here's one good definition. And why I introduced this definition now, not earlier, because it would not make sense earlier. We kind of needed to be exposed to all of the regression models and the fits to go through that to understand, to kind of get more of a feel of what nonlinear equations are. This is one great definition of nonlinear equations, is that when you think of a function, think of the function as a black box that processes some input. You give it input through this x variable here in parentheses. The function modifies the input in some way. It can take the log, and can take the cosine, it can take whatever it wants, and then produces an output. Okay? Produces an output. A simple definition for nonlinear function is one where changes in the output are not proportional to changes in the input. Okay, so in a linear function, okay, depending on the relation between your input and that function, you might double the input, it will double the output. But for a nonlinear function, you don't know. Take the cosine of x. If you double the value of x, it's not going to double the value of the cosine. Okay, it might make it negative. Okay, who knows, right? So that's kind of one simple definition of a nonlinear function, is changes in the output are not proportional to changes in the input. Okay. Now the big question is, what does it mean to solve an equation, whether linear or nonlinear? When we say f of x equals 0, what do we mean by that? I'm going to try to illustrate this graphically. Consider this function. Okay, so again, this applies to linear or nonlinear functions. Okay, linear function would just be a straight line on this graph. But consider this function. It's a highly nonlinear function. In some cases, it climbs very quickly, with small changes in x, but then kind of slowly dip down with other changes in x. It's very nonlinear. If you call this f of x, and if you draw the line y equals 0, remember this blue line is y equal f of x, and the black line here is y equals 0 for any x. Then f of x equals 0 means finding those points in red, or the intersection of the curve y equal f of x and the line, or the curves in general, y equals 0. So solving an equation f of x equals 0 means finding the values of x that make f of x equal 0. Those values of x are called the roots of the equation. So the roots of the equation f of x equals 0 are those.
You cut out again.
Let me see if I have a battery here. Nope. Okay.
Right now it's working.
Now
it's not.
right again. I'm gonna switch to my MacBook microphone, and I'm gonna try to stay close to the MacBook, so you're not gonna see me walk around here in class. Okay. Can you hear me well now on Zoom?
Yes, thank you.
Thank you, guys. Okay. Apologies for this. Pardon me. A chair? No, that's okay. Okay. So, all right. So now we covered kind of the definition. These are some formalities. Again, we're going to go back to the parachutist example. Okay. We're just going through some formalities. We need to define a few things before we get to actually solving nonlinear equations. Okay. So now, visually locate the root of the blue curve. Okay. That blue curve is f of x. Okay. And I want to solve f of x equals 0. So I want you to visually spot the root. Okay. The black line is the line y equals 0, and the blue curve is the function y equal f of x. So you can locate it. Where is it? Okay, it's kind of right. It's kind of obvious right over there. Okay, sorry, it's right over there. Okay, good. Now you know how to locate the roots of a function. Okay, when I tell you find the roots of a function, it almost immediately it always implies find f of x equals 0. Okay. Okay. Now here's another blue curve. Okay. And I am asking you, okay, the blue curve is given by f of x, and now I'm asking you to locate the root, or to solve f of x equal 10. So where is the root of f of x equal 10? Just spot it, eyeball it, okay? And tell me how you would see it. Pardon me? So show me, explain to me how you got that. Okay, so you drew a line. You drew a line at y equal 10, okay? And you intersected that line with f of x, okay? And you found that root, okay? All right, so now I'm going to take that same function. There's a point I want to make here, okay, to unify the discussion on nonlinear method, nonlinear functions, okay? So now I'm going to take that same function. It's the same exact function, okay? This one on the bottom in red was f of x equal 10. Now, my blue curve up there is the function r of x equal f of x minus 10. And I want you to locate the root r of x equals 0. Do you think it's the same as the other one? Yes. So now you draw the line y equals 0. It gives you the same identical root. Okay, what's the point here? The point is that if function f of x equal alpha has the same root as the function f of x minus alpha equals 0. That's all there is. However, taking that alpha to the left-hand side standardizes our discussion on nonlinear solvers. And that operation is called deducing, is called writing the function in residual form. And I have a little definition here for you. The root of f of x equal alpha is the same as the root of r of x defined as f of x minus alpha equals 0. Okay, where r of x equals 0 is called the residual form. So from here onwards, we are only going to work with residual forms so that we write all our function definitions as essentially saying find the root r of x equals 0. Okay. All right. So now take this function and write it in residual form. So I want to find the root of log of x plus cosine x squared equals 3 and write this in residual form. Yes. Okay, so what would you do? So write it as r of x, okay? So simply take your alpha, your right-hand side, put it on the left-hand side, and say this is my new function. My new function is log x plus cosine x squared minus 3, and I'm finding the root of that. And when I say finding the root of that, means finding that intersection with the line y equals 0. Okay? All right, so now we're going to go back to the parachutist. Now write this parachutist problem in residual form. So the only unknown here is c. We don't know what c is. Okay? You're going to assume that u, m, g, and t are given to you. And your only unknown is c. So write this in residual form. You really need to practice that, okay? This is like a classic, simple exam question. Now, it doesn't matter whether you take things to the right-hand side or the left-hand side. It does not matter. The root is always going to be the same value, okay? So here's how I would do it. I simply take u of t, I call u of t as alpha, you know, your alpha, and I move it to the right-hand side. So my residual form is mg over c plus 1 minus e to this minus c over mt minus u of t equals 0. That's my residual form, and I always refer to it as r. So that's the standard nomenclature, r for residual, okay? R of t, or, you know, clearly this here should be r of c because our unknown is c. Okay, our objective is to finally find c. Okay, so let me see if I can if I can edit that. Actually, that's a little typo here. Oops. Okay. Okay. I'll fix that. All right. Okay. So now, again, we're going on some theory to get some idea on how to solve nonlinear equations. And we're going to hit our first method maybe a little bit today. Okay, we can start on it today. So nonlinear solvers are just methods, techniques, and recipes that solve nonlinear equations, okay? For the vast majority of situations, we really need numerical methods to compute the roots of nonlinear equations. In some cases, you can have an analytical solution or you can do a perturbation solution, but for the vast majority of cases, and especially for large systems of nonlinear equations, you really need numerical methods. That's what Excel was giving Nathan, and that's what fsolve was giving Kimball, okay? And so some characteristics of nonlinear solvers is that, or nonlinear equations, you may have 0 or many solutions, just like the curve I showed you earlier. You might find 7 roots, or you might find no roots at all, okay? So we we'll find a way to inspect the function first to kind of see if it has a root or not, okay? Solution methods are always iterative. We're gonna keep refining our guess. Okay, we're gonna start with a guess. We're gonna keep refining it until we get to the root. And they always require an initial guess. Clearly, the closer your initial guess is to the root, the faster you're gonna converge to that root. Similar to iterative solvers, okay? A nonlinear solver is not guaranteed to find the solution, even if one exists, okay? Your initial guess might be quite off, okay? Or you might be outside of the roots range, or you might be bracketing to multiple roots, okay? So you might not ever converge to a root, okay? So it's not a guarantee that you're gonna converge. In general, you do for most cases, but in some cases you'll not converge to a root. And you're like, okay, what am I gonna do now? So, you know, most of the time, it's your experience with the system you're dealing with that helps you figure out a way around this. At least what you're going to be dealing with is not going to be problematic, okay? But for fluid mechanics problem and heat transfer problems, this could be really serious if you can't find a root. It's usually quite serious. Okay. Then solve for the roots f of x equals 0. If you want f of x equal a, then you write it in residual form and solve r of x equals 0, okay? Just like we described. There are two general classes of nonlinear solvers. There's closed domain methods and open domain methods, okay? The idea with closed domain methods is, look, I know I have an idea where my root is. It's between 0 and 2. I don't know exactly where, but it's between 0 and 2. So you set that bracket and you kind of home in on your root. Those methods are guaranteed to converge, okay, if you know your bracket right, if you're bracketing one root, okay? They're quite simple and robust, but you need to bound the root. If you have multiple roots in your bracket, it's going to be a problem. So in a way, these closed domain methods are sort of reminiscent of graphical methods. You kind of plot the function and you bracket the root and you start kind of homing in on it, okay? Open domain methods, on the other hand, the most popular of which is the Newton method, okay, or the Newton-Raphson method, is a general strategy that allows you to find roots of nonlinear equations without bracketing the root. You start with one guess, one point, wherever you are, and it tries to find its way to find the root, okay? It's that simple. It's very, very, very efficient, but is less robust than closed domain methods. But in general, it is the method of choice for large scale type calculations because we really don't know how to bracket the roots in general, okay? We will start with closed domain methods, and the first method we're going to use is the bisection method. And the idea is to make a new guess for the solution at the midpoint of the bounds. So starting with bounds, you make a guess and say, my root is going to be at the midpoint of these bounds, and then repeat. Same idea as finding a letter or a word in the dictionary. You kind of say, okay, it's going to be between this letter and that letter. I'm going to cut this in half and then open it in half and then choose which side your word is going to be in, and then continue repeating the same process. And we will illustrate this method graphically. Okay, so I know that there is a root over here. Okay, I'm going to have to move around a little bit on the slides, guys, on Zoom. So I hope you can still hear me. Okay, so I know that there's a root over here, somewhere between 6 and 9. For the sake of illustration, I'm going to pick my bounds to be 3 and 9. Okay, that's how the method starts. Okay, start with a and b, which bracket a root of f of x. Okay, so this would be a and this would be b. Okay, the next step in this method is to find, remember, you don't know the root, you don't know this one yet. Okay, you don't know this one. The next step is to find the midpoint of a and b. So you define c is equal to a plus b over 2. Okay, so you make a guess for the root, as good as any other guess. The midpoint, you can take 1/3 or 1/4. The midpoint seems as good as any other guess, right? So you take the midpoint between these 2 points. So that's 9 plus 3 over 2 gives you 6. Okay, so that's going to be our new guess for the root. Okay, And that would be C. That would be your new point C. So now you see that, I swear I'm not trying to do pun jokes, but now you see, now you see you have a new bracket, right? You've shrunk down, you're homing in on that root just by taking the midpoint, okay? Now C is your current guess for the root, okay? Clearly you want to check if it's a root or not. What do? You evaluate f of C. And if it's 0 or very small, then you're at the root, right? Because we're solving f of x equals 0 or r of x equals 0. When you find a value of x that makes r 0 or less than your tolerance, then you found the root, okay? So you check if f of c is less than your tolerance or it's equal to 0, then you stop. C is your root. If not, you have to repeat, okay? So if you have to repeat, you have to update your interval. Now visually, you can clearly tell that C is your new A and B is B. Okay, that's your new interval. But numerically in a code, you can't tell that. Okay, you cannot visually inspect which points to take. Should you take C and B as the new interval or A and C as the new interval? To check for that, you take the product f of A times f of C or f of B times f of C. And if the product is positive, then A and C are on the same side. The function doesn't change sign, okay? If f of A and f of C is negative times f of C is negative, then A and C, there's a root between them, right? Because when the function passes 0, it changes sign, correct? You agree to that? You agree that in this case, f of A times f of C is positive. F of C times f of B is negative. So we know that there's a root between C and B, right? There's a root between C and B. So then you can tell that, my new interval, C is going to be my new A, and B is going to stay as B, okay? And then you repeat. You take, so you have 6 and 9. You take the midpoint, 6 plus 9 over 2 is 7.5. So now your new guess for the root is 7.5. Okay, and notice how our interval is shrinking. Okay, and it's gonna keep shrinking and shrinking and shrinking until you hit the root. Okay, so an algorithm for the bisection method will give you the Python code, all of that. We'll do an exercise by hand, but you have to understand it conceptually. We pick a bracket for the root. You should be confident that the root is inside that bracket. You look, you take the midpoint and you check. You take the midpoint, and that's going to be your new guess for the root. You check f of c, is that less than your tolerance? If so, then you found the root. If not, then you have to choose a new interval. Is it going to be A and C or C and B? You check the sign, f of A times f of C or f of B times f of C. You know, if it is negative, if f of A times f of C is negative, then B equals C, otherwise A is equal to C, and then you repeat. You keep repeating until you converge, okay? Okay, so here I have a little comment, solving f of x equals 0. When f of x is equal to close enough to 0, we are done, okay? Close enough depends, again, on the nominal values of f of x. For example, if f of x varies from 0 to 10,000, then a tolerance of 10 may be sufficient, okay? You don't need to get to a tolerance of, 0.0001, right? Although you might get to it quite quickly, okay? And f of A times f of C tells us whether C brackets the root from the left or the right side, okay? So now with this algorithm, I want you to run 3 iterations to find the root of log of x equal to 0, okay? So we kind of know where that root is, all right? But I want you to use the bisection method, okay, to find the root of log of x equals 0. Start with the interval 0.1 and 1.5 and perform 3 iterations. And that's your algorithm out there, okay? Go ahead, do it by hand, okay? This is as good as any example, okay? All the examples you would do, I can give you 1,000 examples, and they're all the same. Okay. Start with A and B, 0.1 and 1.5, and do 3 iterations. Okay, 3 iterations. Start with the bracket, find the midpoint, okay, and that would be update your bracket. You can draw a graph of log x if you want. Okay. Another 2 seconds. Oh, yeah, no, I just wanted to be, okay. Yeah, that's great. Okay, so let's see, let's do it together on the board. So I have the answers for you on the board. Okay. So when you can clearly plot the function, okay, and look at it and try to identify your bracket, how to choose your bracket. Okay, in many cases, this is gonna be the case. Okay, so this is log x, and we know there's a root at x equal 1. Okay, because we know the function log x goes to 0 at x equal 1. And our initial bracket is a 0.1 and b equal 1.5. So then you get your c, your first guess for the root is 0.8, which is 0.a plus b over 2, 0.1 plus 1.5 over 2, that's 0.8. Then you check for convergence. F of c is log 0.8, it's minus 0.223. That's not a tolerance I'm comfortable with. Okay, so let's go ahead and continue. Now, visually inspecting this, you know that your new brackets are going to be 0.8 and 1.5. But in Python, you don't see that. You have to let the code figure this out by itself. So we take f of a times f of c, which is log 0.1 times log 0.8, and that's positive. So that tells us that c and a are on the same side. And therefore, our new bracket should be c and b. Okay, that's going to be our new bracket. Okay, so we take c and b as our new brackets. We call c the new a, and b still is 1.5. And then you compute c, a new c, which is 1.15, 0.8 plus 1.5 over 2. And then you check for convergence. You're at 0.14, still not good enough. So we're going to continue. Now our new bracket is going to be a and c. Okay, so here's how we check. F of a times f of c is log 0.8 times log 1.5. It's negative. So that tells you there's a root between a and c because the function changes sign. Okay, and then we take a and c as our new bracket. So a stays as a and c becomes the new b. All right, and then we take the midpoint. C is 0.975. Look, we're getting closer to 1. Okay, this is great. So we're getting closer and closer to 1. And then you see our error is reducing. F of C is getting closer and closer to 0. It's 0.025 now, and so on and so forth. So now, again, you evaluate whether A and C are on the same side, and they are. So your new bracket is C and B. And you continue doing that ad infinitum. Eventually, your function, your routine is going to take a tolerance at which you're going to stop. And this is where we're going to stop today. Next Thursday, we will talk about Pythonification of the bisection method, okay? And we'll use it to solve the parachutist problem. Thank you. Thank you, everyone on Zoom.